let's talk about hydroboration, oxidation, which is adding water across an alkene. But when we do this, it's in the anti-Markovnikov orientation. So it shows regio selectivity and it's stereospecific. Okay, so let me just show you in this example. If I take something like, this is 1-methyl cyclopentene, and I do the hydroboration, which is with boron THF complex, followed by the oxidation using hydrogen peroxide and a hydroxide base. Turns out, one, that my nucleophile goes on the carbon that has the most hydrogens, and it's my electrophile, the H, that goes on the carbon with fewest hydrogens. This is anti-Markovnikov, so that shows you my regio selectivity. What about the stereospecific aspects of this reaction? Notice that when I add my hydrate across my alkene, it always adds on the same side. So it's always a cis addition. Okay? Now it seems very contrary. How is this possible to do this? So it seems contrary to what we've been going through with the Markovnikov. So let's talk a little bit about each of the reagents first, as we do our mechanism. So let's talk about my boron THF complex. Boron remember, boron only has 3 valence electrons, which means it can only have 3 bonds to it. Not so great, because we know of the octet rule, and we want to have an octet around my central atom. So what happens is, with another boron, it forms what we call banana bond. That is that between 2 BH3s, 2 of the hydrogens are shared. So each of the boron atoms thinks it has an octet around it. I know it's unusual because normally we don't think of hydrogen as being able to have 2 bonds. And in a sense, it doesn't. These electrons are being shared. It really only has 1 bond, official bond to this boron. This one has 1 official bond to that boron. But because of the banana bond, it's not a straight bond. It's been curved a little in order to get this kind of octet satisfaction on the boron atoms. Okay, this is called diborane. It's a toxic, highly reactive, explosive gas. Okay, so normally when we do our reactions, we don't like to work with reagents like this. We'd like to have something that's a little bit easier to work with. Solutions are really good, so instead of having a gas, having something in the liquid form would be nice. Having it not explosive would be very helpful. We can't help too much. We do want it to be reactive. We can't do too much about the toxicity, but if we make it so it's a solution and it's easier to work with, that will probably go a long ways to reducing exposure. So what we do instead is we take diborane and we add in a solvent, typically an ether. This ether is called THF. Okay? tetrahydrofuran. And the lone pair, and I'll need 2 of these, and the lone pair actually will form a bond to the boron. So when I get the boron, so if I look, I'll have 2 of these. You'll have the boron here, and it has a bond to my THF. Formal charges, that's a minus and that's a plus. Because I have 2 of them with my diborane and form 2 of these. This is BH3 THF. Not surprisingly, is a solution, so it's easier to handle and to measure, and it's not explosive. Okay, so that's the good part. So that's why when we do our hydroboration oxidation, we normally don't use diborane. You're going to use the BH3 THF complex. Right, so let's do step 1 first, showing you the mechanism, discussing it, and then we'll go on to step 2. What I'm going to do is I'm going to draw my 2 cyclopentene so that the ring is basically going in the board away from you, and this methyl is coming out towards you. So I've kind of tilted it on its side. The reason is, in just a moment, I'm going to show you what's going to happen when we add in my boron. So I'm just going to draw the boron, okay? Let me just draw it down here, make it a little easier to see. Okay, so surrounded by tetrahydrofurans. But this is my electrophile, right? So my lone pairs will attack that boron. Okay, which means that this is going to start becoming a positive charge, that starts becoming a negative charge. So when that happens, as this becomes more of a negative charge, these electrons will gradually move up towards my hydrogen, or from the hydrogen towards my carbon. So let me just show you transition state for this. So this bond is breaking because what it's doing is it's forming a bond to the boron. Okay? Keep our hydrogens here on the side. This bond to the hydrogen starts to break. So as the electrons are moving from here towards the boron, that means that the electrons here from the hydrogen can now move towards the carbon. Okay? When that happens, remember, this is a slightly positive charge. That's a slightly minus charge. Okay? This is my transition state. This is called a 4-centered transition state. Okay. Now you might stop and say, well, what happens if I put in my boron in the other direction? So let's take a look. So here I have 2 ways of orienting the boron, right? Here again is my 1-methylcyclopentene. But what happens if I put my boron this way? Okay. So you can see I can put the boron either way. I mean, the molecules aren't really going to care how I draw them out, but I'll tell you at what point will they care. Right here. So just as I did that, these electrons attack that boron, okay? And these electrons will come back and start forming a bond right here to that carbon, okay? So my transition state looks like this. Okay, here's my four-center transition state. Now, in this case, again, as my electrons go towards my boron, this becomes a delta minus, and this carbon, since I'm pulling electrons away from it, becomes my delta plus. All right, now, as usual, let's evaluate. This is a tertiary carbon. This is a secondary carbon. The tertiary carbon stabilizes a positive charge much better than a secondary carbon. Therefore, this transition state is more stable and more favorable. Okay? It's the more substituted carbon that has the positive charge. And that's why this doesn't occur. Okay? So, what you end up with So what you end up with is you end up with this improvement. Okay? Notice that these two, my hydrogen and my boron, added to the same side. So, when we look at our transition states and the stability, that's how we know what the orientation, the regiochemistry is going to be. And notice that when we add it, because of the formation of the four-center transition state, we have to add on the same side. We get our stereospecificity. Okay. Now, let's take this and do our oxidation. So we had a boron here. Now I want you to know these two hydrogens can also be used to add onto an alkene. Okay? That's my methyl group right here. Okay? So, what I'm going to do is it adds two more times. Adds two more times. When you do that, I'm going to put R2. That's material cycle. Okay, and the hydrogen is coming out towards you. Here is the hydrogen I added from my boron and my methyl group. It's a 3. Blame it on my cats, okay, but not this time. Okay, so we're going to start here. Now, what are we going to add to it. Let me show you what happens. So, when we said for step 2, we needed hydrogen peroxide and hydroxide. What happens is my hydroxide pulls off the hydrogen to become water. So what you get is this species, which is a hydroperoxide. And water. Okay? And it's this species right here that will attack my boron. Because look it, doesn't my boron only have 6 electrons, but doesn't it want an octet? So this attacks my boron. And notice, everything that we're doing in this mechanism for the oxidation is more oriented towards the boron than to my R group. Now, why do I mention that? Is that important? The reason it's important is that I don't scramble stereochemistry. That's why we always retain our stereospecificity. So now that I have the species, what happens is I actually get a rearrangement. So this bond here migrates to that one, and I kick out a hydroxide. Okay? And when I do that, I'm going to form a borate ester. So let's draw that out for me. Okay, so that was kicked out, forms that. This is what you get. Now, my hydroxide comes back, attacks the boron, and the electrons go onto my oxygen. Have first hydroxide and your boron, 2 R groups, so this will continue to react. Okay, while that continues to react, let's see what happens with my alkoxide. Remember, I have water present. So now my alkoxide takes the hydrogen off my water, and I form my hydroxide again. So the end result let me just redraw that step. I get my water here. Now oxide attacks my proton. That regenerates my hydroxide. get our final product. Okay, so this would be chiral center here, chiral center here. This is trans. Okay, so this is a cycled pentanol. This is the 2 position. So this is a trans 2-methyl cyclopentanol. Okay, so far so good? All right, let's take a look at one more example. Okay. Let's do trans 4,4-dimethyl pent 2-ene. Okay, and we're going to do hydroboration. Oxidation on trans 4,4-dimethyl pent 2-ene. So let's try this out. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. At the 2 position, right? I have my double bond. Okay, and at 1, 2, 3, 4, I have a methyl group here and a methyl group there. Okay, so far so good. And then this is the trans orientation. Okay, so let's go ahead and see what happens. First step, fluorine THF. Second step, hydrogen peroxide. Okay, and hydroxide. All right. So when we do that, look at, really, there's no regioselectivity. This carbon has 1 hydrogen, that carbon has 1 hydrogen. Okay, so let's add the first way. Okay, and it's not going to look very pretty. Let me just tell you, I'm going to draw it. I'm going to rotate it on its side. Okay, so you can see a little better. So when I rotate it on its side, back is my tributal. Okay, so I'm going to put a cis addition, or same side cis addition, on my hydroxyl. So one way I'd have an OH here, and I have an H there. Oh goodness, that doesn't look so great, but let's just redraw this. That's my methyl group. Here's my hydrogen. Hydrogen gets pushed down. Here is my hydroxyl. The tributyl goes in the back. And my hydrogen comes out in front. Okay, so basically I've added my hydroxyl here, I added H here, but it's cis addition. Okay, I could do the other way. So remember, you can say this is it, not a chiral center, but this is 1, 2, 3, 4. This is a chiral center, so plus the enantiomer. Okay, and that would be if I'm adding my hydroxyl on the bottom here and my hydrogen on the bottom versus adding it on the top. But in this case, there is no regiochemistry, so I can add it the other way too. So let's try out what happens if I add it the other way. Okay. If I add it the other way too, let's do the same thing. Add a hydrogen here. And I add my hydroxyl group here. Okay, this one plus the enantiomer. So in this case, you're going to get both types of products. Okay, because there's no regioselectivity based on the number of hydrogens on my carbon. Okay, all right. Let's take a stop here.